Good morning. We're off to a somewhat late start. I'm definitely not totally together. I'm finding myself getting very bogged down with details. In this class, I spent a lot of time since last week not grading papers, of course. I mean, that's become the norm for me in this class. But pushing forward with some equalizer things that I wanted to implement. And then it wasn't until yesterday that I went and looked at my notes for the next problem assignment, and I said I had created all these equalizer things from the last time I taught the course, and maybe I shouldn't have been doing all the things that I was just blindly pursuing. So that's a little bit frustrating to me because I have quite a bit of stuff done already, but I didn't realize it until yesterday, late. I appreciate you getting the problems, and I never even had a chance to post the hints that I had available. I mean, you just keep chugging away, and I'm just going off in many different directions. Joseph is working on his advising. Last week was a big, huge time sink for me in that we had to do our undergraduate advising. So I was assigned 22 names of people to invite to meet with me virtually in my office, and I didn't get all 22 by any means, but I was prepared, and then I was spending a lot of time doing that activity, which I normally you normally don't do that. That's because this is when enrollment opens up for the spring semester this week. So we have to do it for our accreditations that we have through ABET, and we have to hold them to that, so they don't get to register until they visited an advisor, and then their flag gets lifted, and then they can go in and use the system. So I did post a set number 5. It's kind of got some tentative aspects to it, and I'll talk about that. I've also moved forward to get into the next chapter, so I guess the first thing I want to do is just wrap up what we were doing the last time. This stays working, which I guess it will. We were looking at these confidence intervals, and I generally put a problem involving the use of this chart on the second exam, and the second exam is one that I have you do in class. I think I told you that at the very beginning. I could change that, but right now I have it set up to do it that way, and that will be coming up in a couple of weeks. I'm not sure. Well, nominally, I think the last time I ran this exam, it was on Monday of Thanksgiving week, which would be, just to put that in perspective, since we now are in November, it would be the 22nd. It would be that Monday. That's probably what I'm going to do again, but I really don't know for sure. If I decide to make it a take-home exam again, it'll be something different. This is, with only 2 of you in here, it's not that big a deal how I do it, but that will be coming, and there's a whole lot more computer type exercises to do coming up. The final exam will be a take-home exam, though, with some added simulation problems. Absolutely no doubt about that. So I'm not sure I really need to do an in-class exam. I have it, and I've done it in the past, but I'll be thinking about that amongst too many other things that seemingly are on my mind right now.
When do you think set 5 will be due?
I already know. I'm gonna talk about it here, but it's the tentative due date is November 15th, 2 weeks from now.
Okay.
So this has just got it's got a few problems in it, but it involves some more work with simulation. It turns out there's equalizer problems in here. I guess since you jumped me over to that, I'll just show you what I'm still pending on is this decision feedback equalizer mini simulation project. I actually have several other of the problems in here that are already related to using the code that we were looking at last week. So problem number 3, right up there, could go away, and I might decide to put this DFE simulation in there. The problem is mine is not working. I'm debugging it. I've been working on it for about a week. I mean, in my spare time. I think you wrote to me, Joseph, and I said I was working on it, right? I started working on it immediately because I said, oh, I need to get this done. I handed out that one sheet from the book. Remember I gave you last week? Yeah, you have that. And then what I did in that area for myself is I just made a little booklet that has a bunch of pages in it from the same book, but it goes all the way through the section on DFE, and then fractionally spaced equalizers, and what was the other thing that was in there?
So we start working
Passband.
homework, we should just ignore problem 3 for now.
For right now, yeah, until I nail it down. See, and I haven't pushed this out onto the web server because that was I was going to do that before I left my office, but then when my computer came up totally blank in a Macintosh system, it goes through a big ordeal. It says, whoops, something happened. What do you want to do? Do you want to restart everything where it was, or do you want to start with a blank slate? There's an application that misbehaved, and I don't know, it might have just been the cold air and my riding on my bike and jerking it around, but so I didn't really spend as much time doing that, but you'll see what I'm pushing up there. I've decided that rather than you write the code from scratch, I'm giving it to you in a notebook, and that notebook we were using last week has been revised more and more, and I'll push that out there again because it's also referred to in this first homework problem. Only thing we're changing is we're changing the channel that's going to get used, and I'm going to talk some about that today too. It's a very intense channel from a distortion standpoint. And the DFE part I would like to do, but I also found some more stuff on DFE that relates to your work, Joseph, and what you're going to do your thesis on, the SERDES thing.
Yeah.
And it's a complete lecture from the University of Illinois that comes at it from that standpoint and is not traditional digital modulation, but more or less serial high-speed interfaces, and it has the analog modeling and digital modeling, so it has different things in there. But I grabbed it because I said, okay, I'm not going to switch this class and jump way over there, but I should look at it, and I'm going to push it on to you and say, I think this would be good for you.
I think I should watch that.
Yeah, it's a PDF is what it is.
Oh, okay.
There might be a video out there somewhere, but it's a PDF. So I've got that loaded right now. We'll look at it, but this is it. It's a lecture on equalization from this guy at University of Illinois.
Thank you.
Well, you see, that's what bogs me down. You guys don't know me that well, but the problem is my brain runs on so many different things because I get excited about something. So I'll jump over, start working on that, set it aside, say, okay, I'm going to get back to that, but at least I've got a jump start. Another problem I'm working on, do a little bit on that, have that sitting off to the side so I can jump on that. And I have that going in about 5, 6 different things right now. Do any of you work that way? Maybe it's a disease that I have. I don't know. It's like I want to try to do everything, and I can't. So
I know other people like that, but
that's not you.
not me.
Yeah. So I also spent time over the weekend because Xilinx has this ADAPT contest going on. So I joined Hackster.io, which is a website. Have you ever seen Hackster? It's a maker kind of thing for electronics, but it's sponsored by Avnet, which is a electronics parts company. But Xilinx teamed up with Hackster, so I had to join the Hackster website and state my intentions of joining the competition. But then the main thing I wanted to do was ask for a free hardware donation of a Xilinx development board. And the deadline for that was yesterday. So in order to submit to the conference, I had to join, or to the competition, I first had to join Hackster, and then I said, I want to do this part of the competition, and I also want to submit my entry for free hardware, and to get free hardware I had to go read up on the board and pass a hardware quiz. So you had to score 80% or better on the hardware quiz. So I started the quiz twice, and I said, whoops, I better learn some more about this board so I can answer these questions. It says you could take it as many times as you wanted to, but I didn't want to have to take it over and over again, right? What would you do if you were going to apply for something? It's like writing a grant, and the first step is to get the hardware to do your project with. You got to pass this exam, which I thought was reasonable. And then it said, oh, you can take it as many times as you want to. And I said, well, that's ridiculous. I don't want to do that. So I stopped, jumped off to the side, started reading the literature on the board, and then I studied that, and then I took the quiz, and I got a 90%, which meant I missed one problem. So I was kind of like, I wonder what problem I missed. Oh, I guess I don't care because I don't have time to go look, but I got a 90%, and then they immediately said, you're entered, you're in, and you'll find out in 2 weeks if you get your hardware donation for this kit, for this board.
If not, and you probably know this, Digiland has really good education discounts.
Yeah, I use their discounts. I'm already a member of that stuff too. Yeah, they've got nice stuff for sure. And I've gotten their stuff when I've gone to conferences before. One of my Xilinx boards is from them, but I buy other stuff. Actually, a Digilent part is in my proposal. It's an A to D, D to A, little tiny plug-in. It's called a PMOD.
PMOD?
Yeah, it's a PMOD.
We use those in class or in undergrad in one of our labs.
Okay. Yeah, I've been using them, so I want to repurpose that PMOD from another project and put it on this Xilinx board because it has one PMOD connector on it. So that just shows you a little tip of the iceberg of things that I've been looking at, keeping me distracted. So I want to go back to this and just let you know that, you know, I will ask you to do something with this, and if it is a take-home exam, then you'll be able to just plug into these equations or iterate on them to find the fixed point solution to find out, you know, what requirements maybe you need to have. But this function returns out when you give it n and capital N, and then the confidence interval, it returns out those things. And if you spin it around the other way, you can do other things with it. So maybe it'd be cool for me to actually do that as have you use this in a take-home problem, so that way I could make it be more complicated. Because when it's the in-class problem, I just say, here's the situation. I give you this thing, which seems really crude to work with a chart. And I say, make sure you bring a ruler in case you want to just, you know, find points on it. So either way, it's just kind of understanding more about that. So back into the chapter with the equalizers, I'm going to go down a little bit more with that in a moment.
My class has a lot of simulation problems. I feel like I've been working my Python muscles a lot.
Okay, well, it's going to get more. And I'm going to show you some more tools today too. So that's something that I kind of got excited about for debugging purposes. So let's kind of go look at the equalizer, and then I'm going to start on the new chapter. We're going to look at QPSK, offset QPSK, and I found an old Jupyter notebook that entirely talks about the motivation behind offset QPSK, and that rattles my brain because I remember when I showed you a simulation in Julia with a HPA, high power amplifier, causing distortion, which can be dealt with pre-distortion or other means. Turns out I put all that stuff in a notebook and I had forgotten about that. And then I had offset QPSK right after that to kind of demonstrate the significance of it. that was something I got more excited about last time I taught the class, because somebody fired at me from the outside saying, tell me, why do we use offset QPSK? So I said, well, I can tell you because I've used it a lot in projects I've worked on. So what I want to do is we've been using Jupyter Notebook a lot, and I like it a lot. One of the things, and this is the notebook I was going to go talk about here a little bit for offset QPSK, but that's when we start the next chapter. So this notebook is one that we were using last time, and we're going to use it again, and I've updated it quite a bit. It now does have a DFE in addition to the zero forcing and decision directed equalizers. The DFE doesn't work properly, and so whether it's something that I'm staring at in the code and I just can't see it, or what, but I'm thinking if I can't figure it out, maybe I'll just say, how would you like to debug it and figure it out? Or I could just sidestep it and say, we won't go there right now, but what do you think about that idea, that I just give you some code and say, look at this. I will have to give you these pages that I pulled from that book because I'm following that book's lead. I have done DFE before in a work project, in a sabbatical project, but I'm not looking at that because that was done over 10 years ago. So I'm taking a fresh look at it. And you guys haven't been in industry or research for very long at all, so you haven't had a chance for all these years to go by and then say, oh, I did that a long time ago. Can I find it? Can I use that as my starting point? Or sometimes you say, I don't want to look at what I did before. I just want to start with a fresh look and not have that sort of a prejudice on things or bias on how you're going to do it. So you'll find yourself doing that, though. Trust me. You'll say, where's that code, and can I go look at it? Will that help me? Or do I just start reading papers again? I mean, Google wasn't as popular. It was still popular, but now it's even more popular, right? And you use it all the time, and the tools are going to continue to change in that area too. So what I want to do, though, is just look at some pieces of this and then look at it from a different perspective. So one of the things that is out there, I've never showed you this before, but my DSP class, I'm having them use Microsoft's VS Code as a development environment. And so it's an integrated development environment, and it's available for all platforms. It kind of does a little bit of everything, and I use it a lot because I edit my HTML pages for my website. I've used it in C and C++. I've used it for microcontroller debugging and projects with ARM cores. And I've used it for Python. I've used it for learning the Rust language when I wanted to understand that language. I had a student do a project with that language. And then, what else? Well, I won't try to remember what else I've tried to use it for. But the thing about Visual Studio Code is it's free. It is a Microsoft product, and Microsoft tells you that they are monitoring what you're doing with their free software. But it's got Git integrated with it. It's got the main thing that makes it really attractive, besides just being a code editor, is all the extensions that people have written for different languages. An extension is just like a plug-in that allows it to do different things. So I'm not going to spend any more time looking at that page, but I'll just show you what it looks like over here. Generally, when I use it, just so you know that I like using it with the black theme. So generally I like using this other color theme, the default dark. But maybe that looks too weird for a Jupyter Notebook to see everything in black and see all the plots that'll come up in white, like that. So I don't know. I wasn't sure because I've never projected the black background look. I find it to be easier on my eyes, though. how do you want me to run it today? If I run it with the white background, it's going to look like Jupyter Notebook almost, but it's going to be different. You have a preference how you see it? Is this okay, or do you want to see it in white?
I'm indifferent.
You have a preference?
For me, I prefer to be the light.
Okay. I'll gladly do that.
For now, it's okay.
No, I'll gladly do it because I want you to feel comfortable, like, what are you doing? Why are you doing that? You can see that, you know, people are crazy about color themes in the world of software development. So, right? You use tools.
People can spend more time like making their setup look pretty than doing work. I think it's just a fun distraction.
Yeah. Well, I use the Xilinx tools in the sabbatical job, and some of the tools have a default dark background, and the other tools have the default white background, and there it's a lot harder to change your background, and so I just leave it the way it is. So I'm using one tool, it's black, the other one is white.
Vermata is really not user-friendly at all.
Yeah, and I use that some, but I'm using Vitis and then the Vitis HLS, the high-level synthesis tool. But what I want to show you here is what you can also do with this, because if you put the plugins in, or the extensions, and this is your extension library, the extensions that you would install here would be, principally, you would have to put in Python so that you would be able to connect to your existing install of Python, and it gives you all this syntax highlighting. Maybe this Pylance tool, they'll recommend a lot of things. You can see down below here, they're always recommending more things, but this top part of the list is what I have installed. So I have Python, and then the next most important thing is Jupyter Notebook support, which doesn't have a lot of fantastic stars at this point. I mean, every one of these things is rated, like how popular it is, how much people like it. But they've been improving this a lot, and I'm pretty happy with the improvements. It still has a ways to go to be really, really good, but it's pretty nice. This is going to kind of be a hybrid between using Jupyter Notebook, which it really is, and having a full-fledged debugger and syntax highlighting and all these other things that software developers use. And then it has things on the side margin there that are kind of handy too. So these are the two plugins or extensions that you'll have to put if you download it. Downloading it is very easy. You can see over here, well, I already got rid of it. It tells you download it. And I've used it on my MacBook, on Windows 10, and under Linux, and it works pretty much the same on all three of them. So on Windows 10, it works just fine by me. And under Ubuntu, it works just fine by me, and under Mac OS it works just fine. The key bindings and all that kind of stuff change from different operating systems, and you can use different key bindings because the community of users has created so many different things that you can do with it that's mind-boggling, actually. I mean, one that I like is Git History. That plugin lets me, if I'm using this to manage code that's going to put into a repository, then I can see my history and all the changes, and I can see other things that have gone on if I've pulled that in, so I can see all the history. So that's another thing that's pretty handy. But what I'm interested in, and why I moved over to this past week for this Jupyter Notebook, is I wanted to debug and I wanted to watch variables and see what's going on inside. So you have to do a few more steps, and I don't have all those steps to show you right now. I'll have to maybe post on something or find where I got it. There's a setting that I had to put in the Jupyter Lab to allow Jupyter Notebook to allow the debugging to take place. Otherwise, it doesn't do that by default, I don't think. It's such a new feature that they've been upgrading it really, really rapidly. So this looks pretty much like a Jupyter Notebook, but it's not really the same. It has some things that are new and different. It has other things that are identical, and then it's lacking a few things. it tends to be more spun in a different direction. And I think that's just part of life. You got to be adaptable if something seems to be making some headway for you. So here, one of the first things that happens when you open up a new notebook, which I have here, it will say, what kernel do you want to connect to? It doesn't know, it wants to try to figure out any other Python kernels that might be installed on your system. And right now it's not finding the one that I really want to use, which is my 3.9 version of Python. I don't know why, because it was finding it. It's finding the MSys, it's finding a bunch of other ones, but those don't have all the other packages installed that I want to use. So this one does, though. This is a slightly older version, 3.7. So that's, you know, that's the one that I'm using. So as soon as I did that, it said, okay, you now have a kernel running, and it's also a little bit slower than the notebook is. So it just ran all these initialization cells for me, and now I can start using these cells. So I'm just going to show you a little example of what it can do at this point. And then maybe I'm going to jump over and show you further down in the notebook where I have the decision directed. I've got to push this up to the web server. Right now, the old version from last week is still the one on the web server. But suppose you want to run a bunch of cells like this, and maybe you've got functions or other things that you've written, and I'll show you that in another step. But if you just want to run a cell, and rather than run the entire cell by hitting Shift-Enter, which is what you do in the notebook right now, right? You're using it where you just have a code in a cell, and you have your cursor in the cell, and you go Shift-Enter, and then it runs that block of code.
In Jupyter?
Yeah, in Jupyter.
Yeah.
Yeah. Same thing happens here, but another option that you can have is I can turn on the debugger. So if I go up to here and just say debug this cell, it will launch the debugger, and then it's bringing me to that breakpoint. And then I have up at the top here the ability to step down. So I'll just step one line of code. And now this line of code has just been executed. So if I hover over it, I can see what are the variables inside of it. If I went to the debug console, which is open down below here, I can also, and it's using all this automated IntelliSense syntax highlighting. So it'll display that instantly. So you can go off to the side and kind of interrogate things as you're debugging or as you're working through a cell, which is what I like to do when I'm writing C or C++ code. So then you can continue stepping this. I could set another breakpoint. I could just run. I could step into a function. I should be able to, in theory, right here, I'm sitting on a function that's in my library, SIGSys. So in theory, I should be able to step into, and voila, it went right into the module sigsys.py, and it's right at that function definition. It's this function right here called discrete impulse. And if I don't want to go into that level, I can step back out again. So I can step out of here, and I think now it hasn't really stepped out. Yeah, it has. It stepped me back out again, and now I could continue to step down. And now at this point, it's not really going to, because in this code, it's doing plotting things. It's going to delay showing anything that you would normally see in the notebook until I would fully execute this. So if I run here, I'll just continue to run the end of the cell. Then the debugger will stop. And then I'm going to turn that terminal window off, and then I'll have my plot, just like you would normally have in Jupyter. But you can go and interrogate things and maybe figure some things out that you're just not sure what's going on. Otherwise, you have to resort to other techniques like printing or doing other little things, which I definitely enjoy doing in Jupyter. I'll take a little piece of code, create it in another cell, test something, figure out how to make it work right, and then I'll move it up into the main code cell where I'm programming something. This just gives you some other options, and in doing simulations, you can do fancy things with your breakpoints. So I didn't show you that, but if I right-click over this breakpoint, I can edit the breakpoint, and then I can put an expression in the breakpoint. I can do a number of different things. I can have a hit counter. Don't stop here until I've hit it 50 times. And if you're doing error probability checking or waiting for a transient in a simulation to go by, you could do things so you're not going to stop and start debugging your code until you've gotten far enough in that things are now, the action's starting to occur. I'm sure you've done this, a lot of stuff with debuggers in your development, or maybe not, I don't know.
I have back and forth, but now
For me, it just goes, I go around, like some days I'll use it, some days I don't, sometimes it's just really critical. Signals and systems analyst type people, and I'm going to say that's you, because that's about the only thing I know about your background. I know that's what you're studying. We don't generally do that. I didn't get into using debuggers. My wife is a software developer, and she taught me at a young age, right after we got married, she said, learn how to use the debugger. It's going to be so important if you're doing a lot of code writing. So I then started learning debuggers every time I got into a new language, because I said, okay, maybe she's right, and she's a very sharp engineer. I would not want to work for her because she's very demanding also. So this is an example of where you might find it useful. Sometimes I don't resort to it usually first off. I try other means. I try to just look at the error messages and write little test cases in Jupyter cells. But sometimes if it's a bigger length thing, I like to just start using a full up debugger so I can play games like this. And it also gives you some reassurance. I've mostly used expressions where you can put a condition in here. Any type of Python expression can go in here, and then it will stop only when that condition is true. Hit count is pretty simple. Log message, I probably should learn how to use that, but I haven't. That sounds like it'll log a message of some state when it hits that, and then it won't stop. It'll just log it. I guess you could use that probably for error rate counting. I don't know. I've never really thought about that, but it automates things is what it does, though. So let's see. I just deleted that. No, that's right, ND. So let me just go down here and show you how I'm stuck, and then I'm going to leave this behind. The other nice thing is, just like in the Jupyter Lab, we have an outline. So here, the outline is looking at markdown cells just like it does in Jupyter, and I can see what I have in this notebook already, and most of them are currently expanded. If I want to suck them all up, I could hit the minus sign here, but I want to go down to where I was developing the decision directed. All the code is at this location, so it's just taking me right down there.
So you're saying your FIR worked, but your IIR didn't?
In what we were just looking at the beginning?
Yeah.
Yeah, so this is my brain on steroids. I just jumped off of that. Let me go back to that. I wanted to point something out there. No, they both work. Yeah, so I'll go back up there. Channel models. This was important unto itself. You can also hide things too. So if I move over here and right click, I can collapse the input cell so I don't have to see it. And then I know it's collapsed because of that. Well, something in here is going to tell me it's collapsed. Expand cell input if I right click. That can be helpful. My screen that I work on is a lot bigger than this. This one's like super cramped. I can't do much with it. Yeah, Joseph's question was channel model. This is what I was using last week. I was using a Butterworth filter, and it was being used at the sampling rate of 16 samples per bit or per symbol. So there's what that impulse response looks like if I was to change my plotting here and just put /16 in there, or actually divide by ns, what did I do? My fingers hit something that I didn't want to hit. Yeah. This keyboard is so tiny that my fingers tend to always bang into the wrong thing. I wanted to be over here. See, the IntelliSense is trying to help me, and there's an NS way down here that I have coded in there. It takes a long time, it's slow, but this is, from a communications theory, this is the stuff that we're interested in. How long is that impulse response in symbols or in bits? And it's pretty active over about 5. So it's spreading energy that's coming through the channel over about 5 bits worth of information, which is causing the eye pattern to close up, and it's kind of aggravating things for us. The first couple of the homework problems use a very different channel model. Dr. Zemer gave one in the homework problem, but I didn't like it, so I modified it, and in this homework problem I've modified it. That died away. I'll have to open that again. I've modified it to look like this, but this is a channel model in terms of bits. It's not per sample, it's per bit. So because we're doing everything, we were doing bit-spaced or simple-spaced equalization. So that is the weights of a real impulse response. So what I'd like to do here, I would like to in the keystroke control / comments and on-comments lines. So I'll on-comment those lines, and now I'll just run this cell again. And why is it taking so long to plot? I don't know. I find that's one of the things I don't like about this. It's kind of slow compared to the straight notebook. But at any rate, what I did to put this on an equal footing, you can see what I'm doing is I'm upsampling by the NS factor in here. And I could have made that say NS. I just left it at 16 because I was tweaking this early this morning. But this is how I can represent it, and then I can actually use this in the channel if I want to. Even though it's upsampled and it has images in it, it's still a useful means for modeling with the symbol-based equalizer, simple-spaced equalizer. So now this channel is a lot uglier looking. It's got a bunch of delay in it, which that doesn't really matter. How the signal energy gets shifted on the time axis, that would be part of propagation anyway, but the spreading on this is considerably worse. You can see there's a large sample of 1 at 8 symbols in to the impulse response, and then there's some precursor stuff from the channel, some weak reflections that are coming earlier due to things that can happen in propagation modeling, and then there's post-cursor type stuff happening after that 1 at 8. And so this is used in these problems. So I'm just showing you how that could be integrated. And right now in my channel, what I did is I go inside my functions and I just comment out this Butterworth filter, which was in there, drop this piece of code in here, and then just use that as planned. So it would show up down below here. Let's just look at the decision-directed equalizer. The decision-directed equalizer in its top-level function call is right here, and here is currently where the Butterworth distortion, channel distortion model was located. So this would just get subbed out with what was up here. Let's go and get back up there. And so this is how I ran those first few homework problems, is I just made this substitution. And it's in the zero forcing model is where that is being used, but the zero forcing code has the same top to it. So I would put that in here. The tabs are not where they're supposed to be because this is inside of a function, so it's tabbed over. And then technically I should comment that out if I want to. And now it's just going to send things through, and by having this upsampled, this is going to manage things accordingly to NS. So I'd probably want to put NS in there if I can make my fingers work right. If I wanted to go that way with that. And then if I drop down here, you'll see where I'm stuck. I don't want to run that right now because this I have to reevaluate whether or not I've got something else that I need to fix, but let's just do this. This is what I was running last time. So now I can run a simulation, and the types of things I was doing last time, I was saying let's just look at, this will be 5 taps either side of the center, so precursor 5, postcursor 5, and then there'll be a tap right in the middle, so it's 2 times n plus 1. That's this calculation over here. And this second argument is mu, which is the convergence parameter in the LMS, remember from last time? If I set mu equal to 0, then the filter will never get a chance to adapt. I'll just hold it in check. I'll say, can adapt, mu is 0, it can never change the filter coefficient. So what that will do is, I've initialized the filter like this. These are the initial filter coefficients. Just 1 in the center, 0s either side. I'm saying just make this a no equalizer. And if I set mu equal to 0, it's never going to be able to equalize, right? So I'll just run this case through. So this populates a data structure, decision-directed input data structure, and that's this thing right here. It just holds n and mu, and where I'm going to start counting errors. I could start delayed if I want to because I've got time for the equalizer to settle and so on, so I could play with that if I wanted to. So that data structure is just used to create a single variable that I can pass in. That's its sole and only purpose is to just make my call list shorter. Does that sound okay? In MATLAB, I would have used a data structure also. MATLAB had a struct type of variable where you could say a dot something and then set that equal to something, and a dot something else. So this is serving that exact same purpose. But in Python, you have to do it a little bit differently. And Joseph, you made the right comment because I had forgotten that was exactly how I had used it. But so you have to create a blank class that doesn't have any methods. It just has the init function, or the init method, which you just call it by the name of the class, and then you can have this function runs and it fills up the fields of the data structure. The 3 fields in this case get filled in. Likewise, I have another data structure, decision-directed outputs, that gets filled up with these variables, and that makes it easy in my equalizer over here to have it just simply return at the end of this. It returns some instant variables. This is the top level function in the simulation called shape PSK, decision-directed equalizer sim. It returns some instant variables for error probability assessment. It returns the equalizer output, so I can plot an iPlot immediately. But then if I want to get some more detailed information about what went on during the simulation, that variable holds a bunch of other pieces of information in this data structure that you can then use for doing plotting and other assessments. And of course, the top level function is calling DDLMS inside of it here as appropriate and doing, different things. And Python's really nice like that compared to MATLAB. MATLAB is so old-fashioned in my opinion. When you first learn MATLAB, you say, I have to write a .m file for every little piece that I want to do, and then you have all these little .m files floating all over the place, and they become a mess after a while. So what I like about Python is you can have just one .py file, and you can have all these functions inside of there, or classes, and it's all organized. It just makes it nicer to me. MATLAB, you can get around that too, and I've learned how to do that in a more modern twist on things. But it's because, only reason why I now know how to do that is because I forced it to happen. If I have to use MATLAB or Octave, I will try to organize it like this. So this is all in one cell. It's just for convenience. And so now I'm going to run it, and I'm going to force it to not adapt. And okay, I know what went wrong. I'm using the old version of Python, which has the old version of my package installed in it, which had this as capital NRZ. You guys can't get access to it, but I have too many installs of Python on here. So what I have to do to fix that, I will just change that one function, and it's right here. Then I'll have to change it back again later. It's also going to hang up on this. This was AWGN. Why do those names change? It's because my co-author decided the package should have lowercase, because that's the Python standard, I think, language standard.
It's more Python to use lowercase.
Yeah. I was being more of a signals and systems person and using capitals for things that are capitalized as abbreviations in COM theory. So I got caught into that trap. So I'll rebuild this. See, it compiled fine, but it was giving me a runtime error. So now it should be okay. So it ran, didn't find any errors, and now what I can go down here is I can just take a quick look at my iPlot, and it's having some problems with symbols. In the newer version of Python, I didn't have this problem. First time I really ever noticed this, but ignore that for the time being. I'm not really sure why it's complaining about that, but at any rate, I'll put in a reasonable value of mu, which I had suggested here would be 0.005. So I'll rerun the simulation, and now it's going to be able to adapt. And if I look at my iPattern plot, it's doing something because it's adjusting coefficients. And further, I could add some more code down here, and I could go dd output dot, and I could get a look at that guy right there. AOPT is the filter tap weights, and they're complex because the channel could be complex. In any case, that's what it's adapting to. And if I was to turn off the equalizer, of course, this is just a good test that I've been doing. If I was to turn off the equalizer, rerun the simulation, and then just go down here and look and see, have I succeeded in keeping my initial values? Yeah, I have, right? Does this make sense? Just sort of quick debugging, rapid debugging, stay on top of the game. And then this was stuff I did. The typing is all messed up here. I've got to figure out why I can't get access to the newest version of Python. But what I want to do now is just drop down to kind of where I'm stuck in my code, and then
time.
Mm-hmm.
I can imagine, and maybe I'm wrong, if your SNR is too bad, I could imagine that decision directed would never converge because it would just keep adjusting taps based on bad decisions.
Correct.
Is that right?
That's right. But then people say DFE. Remember, I gave you that one pager.
Right.
In the pager that I gave you, it said DFE has less noise in it because the precursor values, you know, the main impulse response is here, and then the little things that are ahead of it are still done with the decision directed from what's coming in, but then the post cursor is fed back using the hard decision values, and it's free of noise then. But in both cases, yes, it has that problem with the decision-directed aspect of it. The decision-directed is separate from decision feedback. Decision-directed just says that it's making hard decisions, like the block diagram shows, and then some of the taps are driven with that. But
I guess you can start with the training pattern to get somewhat good.
yeah, exactly.
And decision directs to refine yourself or something like that.
Yeah, that's right, if it's really bad. And you're going to be exploring this, and part of what I'm going to have you do in this set number 5 is you're going to explore, and you're just going to notice things. You're going to say, wow, this doesn't work very well, or this is interesting. This can get dragged out into the weeds somewhere, which is why I was just showing you what I was showing you right up here. I mean, these pictures are really nice. Again, the fonts are messed up on here. I don't know why that is, but this is something that I find really useful, just displaying what the tap weights are. And this has got a bunch of things that I had in this notebook. I'm kind of hacking it up a bit. But to see what's going on, I mean, if it's not converging correctly, and you can see that I'm starting it here, well, one of the things about the equalizer that you can do is you could start it with all zeros and then let it try to figure out what's going on. But I think a more traditional way is to start it at a nominal value, like the benign channel case, and then let it find its way. But in anything with a gradient descent, and I think neural networks have this same problem, you train them with large sets of data, right? And then it knows something. We're starting this, if we start it with all zeros, we're like, I'm not telling you anything. You have no clues as to what's coming your way, and it makes it very challenging to do that. It's a blind form of equalization. So I think what you said, Joseph, is right. I mean, if you're blind, you're going to just literally do dumb things, and it's possible that you'll pull yourself out of even something that's solvable, and you'll never be able to fix it. I mean, you'll get dragged out and never get in the right spot.
And I think one more related question I had was, I think in machine learning, what they tend to do is they start with randomized taps. So they'll randomize their tap matrix, and I think the reason they do that is because you can have many different local minima, and so sometimes they'll like run with different random taps and train in parallel to see which local minima is lower.
Okay.
You said that this kind of a system doesn't have a local minima, right? It just has an absolute minima. So it's just a ball.
That's right, because of the mean squared error criteria. But the thing that can be confusing is the decision-directed aspect of it. That can make it get confused. It doesn't, because of those errors, it can get lost, is what I found.
But there aren't like a local minima where it can get stuck in.
There shouldn't be, but noise, because gradient descent has got this problem where it can just hover around. It may kind of get hovering over here, and it doesn't get over to the right spot because it just keeps getting beat back by the noise in the gradient descent. So the solution to that then is what? I mean, this is something that you can play with, and you'll probably want to play with. The solution to that would be make mu here smaller, make it smaller than 0.005, so it takes really tiny steps, and it can't jiggle around a lot, but it'll take longer to converge. which is why I have this other argument up in here, end start, so it doesn't start trying to do error counting until it's gotten more stabilized. And of course, yeah, you can look at that, and that was done in here. Here we're looking at mean squared error. That will run slowly again. That's what it was doing here. It converges pretty rapidly, and then this is just the tap weight noise. It has to do with the step size. I think I should demonstrate that too now that I'm doing this. So run this one. It's the plotting that's taking a really long time for whatever reason. Okay, so that's got all values in it now. So what I'm going to do here is just plot that. And I'm going to plot that. That's the error squared. The case we were looking at was for a higher signal to noise ratio. It's just another example that was in the notebook here. But if I was to, and it's, yeah, the error is complex, so it was complaining about that. I needed to do an ABS around that first. Okay, so, and then it's gradually getting tinier. If I make that even smaller, though, I think we should see, suppose I make that 0.001 and run this, and then just look at the error. I could overlay these, but I didn't think to do that. There, it's taking a lot longer to finally settle down because I made it 1/5 as small. It's still converging way out at the end of 1,000 symbols. Okay, so back to where I was headed. You can see why I didn't get a lot of things done is because I was fiddling around with this a lot. This is the decision feedback equalizer section that I put in the notebook. So I relabeled everything to have DFE in it, and then I tried to put in, these are the attributes that are in that page that I gave you. This is the number of post-cursor taps. Is following the block diagram notation. The only thing I did different from that page I gave you is I let n be the number of precursor taps plus the center tap of 1. So there's n taps up front, 1 idealized tap, and then there's m post-cursor taps is the way I set this up. So drilling into this, I created a couple different variables, and there's some things about this that don't work, like I said. I mean, it actually, it doesn't not work, it just doesn't work very well. It actually pretty much doesn't do anything. So I modified everything else in here. So this thing is also going to crash because of the fact that I've got the wrong variable. So that has to go AWGN. And then this needs to be NRZ. Okay, so it just compiled. And now I will it runs, and these are the initial tap configurations. So there's 5 precursor taps. There is the desired initial value for the center tap, and then there's 5 post-cursor taps. And seen this before. This is just going to be I'm doing too many. Putting too much into the iPattern plot because this computer is slower than my MacBook is.
Yeah, it doesn't look like it did very much.
This is no equalization yet. I have to turn it on. This is just nothing, but I would have to turn it on like 0.01 or 0.05, let's say. Rerun this. And now if I look at what it's trying to do, I can kind of diagnose it and I can see how far. This is at the end of the simulation where it's putting out my taps. This is the one that was 1 J0, so that is still very large, and then we've got some small values either side of that. But if I go ahead and do this picture, and again, it's going to take a while to plot it because I'm plotting everything. I mean, I'm plotting all the traces in the eye. There. It hasn't really done anything very useful. It's changed it, but it's not at all right. And another way of looking at it is to look at the sample values that would come out at the symbol spacing, and these values should be strong plus and minus ones if the eye pattern was really totally open. Instead, they're hovering around, and with no noise in the system, that's not supposed to be happening. So what I was doing to diagnose this, though, I was running what I was showing earlier, and I just want to show you how the debugger was helpful for me here. So I was putting a breakpoint right here. And then I would go into here, debug cell. It's going to run to this breakpoint, but the first thing I want to do is then jump into this function. So I'm going to say dive in right here, step into, and it's going to take me up above where I'd written the code, and it's taken me to the first line of the code up above. And then I can start following my way down. So for example, when I get into the LMS equalizer, I'm setting up some variables in here. To hold the states, I'm holding the precursor and present states, and I'm stacking. This is how I'm going to step this in time, but I'm initializing them right over in here. And I was experimenting with initializing as complex or not as complex, thinking there was something silly going on. But I could just stop in that initialization. I could hit run, and it's going to run to that point, and then I can just take a look. What are my states initialized to as soon as I run this line? I can see what the zeros are, or I could open up down below here and just see, well, I could just see what those states are, but they're all zeros anyway. I know that. Oops. What did I put in there? I don't think I put the right thing in. Now I forgot, I need to hit tab. I'm hitting enter and it's not doing anything. So I need to say states, hit tab, and then it completes it. So that's the initial values for the states all put together, the 5 either side and then the center. So I'll have this up later this morning. I do have an 11 o'clock meeting, so I won't get it up right away. But I wanted to just point out to you how you have another dimension. You can try this debugging if you want to, as opposed to the other way of just writing it in Jupyter. It maybe you'll get excited about it, maybe you won't. The only way to find out is to try it, though, and you might like it. I've got to figure out why some graphics isn't working right here. It was working fine on my other computer, but and of course the terminal that's sitting in here is available. You can just run Python from the command line right here if you wanted to. You can open up multiple terminals if you wanted to. If you go into here in this Jupyter tab, you get to see all the variables that have been declared in your workspace so far. And then if you want to click here, it will pull them out. I don't know what it's doing right now. It'll pull them out and put them into a little array if you wanted to just look at them. I'm not finding this to be particularly useful for me, but they're trying to mimicking things that MATLAB has, because MATLAB has the workspace variables that you can look at in another index. Right now, I'm going to stop the debugger. I'm just going to disconnect from it, and it will kill it. Data viewer. It's a work in progress, though. And it's not being driven by people like us three. It's being driven by the data science community to develop these tools. They're just making all this stuff happen. We count for about 0 on the map. But that's okay. We can, I don't know. I'm fine with tagging along where the money's at. I mean, not where the developers are at. If the tools can be useful for our purposes, then we can do things with them. I think last week a new version of this came on. It was supposed to be more stable, but I don't think it's very stable right now. So before we get into the next chapter, I'm just briefly going to look at what I found in these slides, only because of the fact that it shows you that we've tuned into one aspect of equalization, mostly for COM theory and the traditions of that I've grown up with. But this has the same title. And I'm just going to look at a couple pages and you're going to say, wait a minute, what are they doing? And you know, the reality is everybody drills onto their topic. There's so many topics out there, and you say they must be useful for them, and they've drilled into it from this point of view. It's just showing you the diversity, I think, that it's not a simple matter. So this is exactly, I think, your gig, right?
Yep.
Buses and signal integrity issues.
I guess one interesting thing about a bus is you usually don't modulate on a carrier at all.
Exactly. But that's fine. I mean, I have my first PhD student went to work for a company called Cirrus Logic, and he was working on the magnetic channel, encoding and decoding things on hard disk drives when he first started his job. And it was a communications channel. He was using communications theory, but he was working in baseband for a magnetic channel, recording channel. And this is a channel also. So it ends up being legitimate. It's just what you grow up doing. So this is very physics oriented, and they're saying channel impairments, reading and writing from a controller through a circuit board, and this guy drills right into what some of the issues would be in the signal integrity and so on. And equalizing a channel with pre-emphasis and de-emphasis. And I'm going to pretty much stop right here, but this is definitely a different level of detail. This is the circuit's level of detail, but the channel is still impairing the ability to communicate. So I forget whether there's another picture. So his decision feedback equalizer is totally different than the one I showed you in that block diagram from last week, because this one shows that all of the taps are after the hard decision device. That's the triangle with the hard decision, you know, the comparator kind of symbol in it. And that's being fed back in, and it's trying to adapt that with the serial data coming in. So this is probably what you're interested in now, or maybe what you're interested in, I don't know. So it's kind of cool. You just have to kind of look at it from another point of view.
I imagine it's much cheaper in hardware to put the taps after the hard decision, because it essentially saves you multipliers. You just put in A or minus A.
Something like that. And that's not stuff that you have to do, but you're working with that community is what I'm guessing.
Yeah.
So you want to fit in with those guys.
Well, we want to make sure it's like implementable in hardware.
Yeah, and I found another article on that too. It's a whole different ball game, but I'm willing that this is how I get myself spread all over the place. I don't stay in one little spot. I say, oh, if I'm going to accommodate like you doing your work, I'm going to try to adapt to it, because I'm a firm believer in trying to not be ignorant. I mean, if you take the view that we're taking in this class and then jump over to that community, it's like, what are you talking about? Where did you come from? You don't have an understanding for how we look at things, so you kind of have to adapt to their terminology and their issues, because their issues are very real, and we might be ignorant of that stuff. And if they came over to our side, then they'd be way out of base too. So it'll be like that all the way through your career. You have to adapt to the new problem and kind of read some of the papers that people have been using to help in that area.
But my guess is that on PCBs you have more SNR, and then you just start to run into like parasitics where you lose bandwidth. That's my guess.
Yeah, and
Which
it
is
causes.
why they're moving to PAM. That makes sense.
Yeah, and I got an email from Keysight over the weekend saying I can attend a conference after it's already taken place, and
Oh.
there was one session that was all about PAM4. So that looked interesting to me, but I didn't go off into that thing over the weekend. But you probably should be looking at it if you haven't. It's probably people that you know that were in that session.
Yeah. I get these emails after the fact also.
Okay.
I don't go to them live.
Yeah, well, you can go sign up for it, and then you can get the link to watch it. So probably, if you don't have it, I'll see if I've still got it. I can send it to you. So we're moving on to M-ARI Datacom systems in this chapter, and then a lot of other miscellaneous modulation schemes and multiple access schemes and things of that sort. So the very introduction here is just going to quadrature multiplexing, as Dr. Zemer likes to refer to it. It's eventually going to lead to full-up M-ARI signaling, where we can put symbols up, and then there's M levels to those symbols, and then we can put that in 2 dimensions, and we can get all these other things. The starting point, though, and this was an idea that's in COM 1, when he talks about quadrature multiplexing on page 206. You don't need to jump back and look at it, but how you can, fundamentally what we can do in the carrier is we can modulate the in-phase axis, which would be the cosine carrier, and then we can modulate the vertical axis, which would be the sine carrier. So that's what quadrature multiplexing is. And it could be analog or it could be digital, as he pointed out in that page in the book. So this would be a quadrature multiplexing device for phase shift keying, and this is the picture that he's got in the book. Quadrophase shift keying is one of the oldest digital modulation schemes. It follows BPSK, which we've been looking at, where it shifts between 0 and 180. So quadrophase shift keying takes on 4 different phase shifts, and the bit stream comes in and is demultiplexed or serial to parallel converted, and then you have a bit stream that's running on the sine carrier and one that's on the cosine, and then those get summed together. And in this fashion, this block diagram, this is also old-fashioned, but this is purely an analog implementation where you would use analog multipliers and then have a power summer at the output there. Of course, if we're doing this today with a modern transmitter, it would be complex baseband, and it would be real and imaginary parts. So that would be the major difference for us. So quadrature is the imaginary part, and the in phase is the real part, in our complex baseband notation at least. And then if we were modeling that as a transmitted signal, like I said, in complex baseband notation, we'd be able to take the two message streams that are on in the demultiplex mode there, M1 of t and M2 of t, which are effectively what he's showing here. He didn't, I think this was back in chapter 2 actually, or wherever it was, whatever the chapter was I referred to. So M1 and M2 can be analog schemes. In this case, they're just binary digital. And then we have the envelope form. So this is the envelope and phase form, and this is the I and Q. And right now we're interested in the in phase and quadrature. But other types of modulation would be envelope and phase might be of interest, like in modeling of phase shift keying. You might just care to look at the phase, or and the envelope R of t would be something that you're looking at as not being good if it's a constant envelope scheme, but you go through a non-linearity, let's say, which is why we'll be looking at offset QPSK here in a second. So ideal quadrature modulation schemes, the in phase and quadrature, are orthogonal. So it's like having two separate channels available when you're doing this sort of scheme. You can independently send information on the in phase, independently send it on the quadrature, and this was very useful in early satellite communications because they would send, one channel. They could actually have mixed data rates. You could send one data rate on the in phase and a different data rate on the quadrature, and just a lot of things were done in SATCOM in the earlier days. Nowadays, especially in terrestrial or cellular, we don't even think like that. We just think we have the in phase and quadrature, and we're sending IQ on it all the time. But even, we're going to eventually be looking at OFDM, and that is very, very popular these days. It still reduces down to the individual carriers of OFDM have binary phase shift keying, QPSK, Emery, quadrature amplitude modulation on those subcarriers. So it still is built out of the same pieces that we're looking at right now. It's just put together differently for a different reason. So this is the connection between the M1 and the M2. And then if we assume independent bit errors between the two carriers, the in phase and quadrature, you can talk about the probability of a correct bit or a correct symbol is going to be that you're correct on the in phase and correct on the quadrature. So there'd be 1 minus these complements of the error probabilities. And then if you write that out, let's see what so that's a probability correct, and then this is the complement of that. So that's the error probability. And I think, let's see, eventually when you clear through here, there's a few problems from chapter 10. And this problem right here is looking at that. The fact that the symbol error probability of QPSK related to the bit error probabilities of the in-phase and quadrature, and what does all of that mean. So it asks you some fundamental questions. So if you haven't done that before, you'll get a chance to look at that in that homework problem. So the way the demodulator works for QPSK is just you essentially have two separate integrate and dumps if you're using the rectangular pulse shaping, or if you're using the root raised cosine, you'll have two separate detectors. Again, these were the pictures from the book, and these are the traditional ways that QPSK would have been defined for space systems in the very beginning, and it's just an analog-based scheme, but you have two integrate and dumps, and then you're making decisions, and then you remultiplex the bit streams back together again. And that's then when you have the serial bit stream. So if we're assuming the carriers are independent, then the noises will be independent because they're in quadrature. So we have a decision statistic that looks like this. Oops. Didn't want to do that. Just remember the notation. The cosine is the in-phase and the sine is the quadrature. So those are our decision statistics, and then those can be used for the tail probabilities to get the error probability. The noise variance is just like we had before, in phase and quadrature. Let's see. And so when you come down to computing the error probability, you've got one bit of difference in here, though. If you look at this equation for the probability of error, a 2 is missing, and that's because of the fact that the energy is now different. And let's see, here's the plot of it. It's because in QPSK, the individual bits have half the energy of the total symbol. In other words, if you have ES is the energy and the symbol, it gets split equally between the two bits in the typical quadrature system like this. So that pushes the error probability curve out by 3 dB. And then you had the additional error that you get on the symbol error probability, because it's that 1 minus the probability of being correct on each of the two channels. So that's what this plot is showing you. And this plot is a little bit confusing, because for the BPSK, that's the bit energy per bit, and for the QPSK, it's the energy per symbol. Again, this is what's swirling around in that homework problem that I pointed out, the very first one I assigned out of Chapter 10. It's just something good to look at, because it's something that people, I don't know, I feel like they try to get you confused about things. But one of the inherent advantages, what we'll see, is the channel efficiency, is that quadrature amplitude modulation does not use more bandwidth. So if you're using B hertz of bandwidth for a BPSK scheme, you would be able to use the same B hertz of bandwidth for the QPSK scheme, which means you're getting twice as many bits per second per hertz of bandwidth with QPSK. It does have this difference in symbol error probabilities. It does have this difference in energies being split like that, but you get the efficiency. And if you look at the bit error probability of the individual channels, it's the same performance as BPSK. same exact performance, ideally, as long as they're in perfect quadrature and there's no crosstalk between the two channels. So you get a really good bandwidth efficiency, but you have more complexity and you're more subject to some of these errors.
I assume that a receiver could still have a rotation problem, right?
Definitely, it has.
Which one is I and which one is Q?
Yep, it's actually a worse problem. Thanks for reminding of that. So in QPSK, it could be like this, or it could be flipped over. So you have to flip it to resolve the ambiguity. With QPSK, you've got 4 different possible badnesses there. So you have to resolve the ambiguity in a bigger sense. And all modulation schemes have, higher order modulation schemes have ambiguity issues that you have to think about. So a variation of QPSK that came along, and I'm going to introduce this, and then I'm going to talk a little bit more about it. If I can get this example running in the Jupyter Notebook that I created while you're on break, was to create offset QPSK. And offset QPSK, the main feature of offset QPSK is that on the quadrature modulator, you're now putting a half symbol delay or a 1-bit delay on the quadrature channel. So you're going to stagger it. It's also known as staggered QPSK, but I like the name offset better because that's, I think, a more popular name, but sometimes they use the term staggering. So you can see that the 2 data channels are flowing with the transitions occurring staggered or offset by half a symbol, which is actually just 1 bit. So fundamentally, and this is what I want to look at, fundamentally what QPSK does that's bad is because the bit transitions occur synchronously on the in-phase and quadrature. This IQ plot is showing you that the waveform, if they both occur simultaneously, which is number 2 in this picture, then we're making the carrier have to pass through the origin. And that means the carrier has to totally collapse down to 0 and then come back up again. And if there's a nonlinearity in the system, like a high power amplifier with compression, making the carrier envelope totally shrink to 0 for a moment and then come back up again is going to cause more problems than if you go with offset QPSK, which never has both transitions occurring at the same time. And that's what that IQ plot down below shows you, is that it never has to go to the origin. And that is very helpful when you have amplifiers that are running in compression, slightly nonlinear. I guess I'll just do this. Maybe I won't get the simulation running. These are pictures that came from the Rice book. So when you bandpass filter QPSK, band limit it, then these are the things that happen on the left there. You get those little goofy looking things in the time domain, but you're seeing primarily that it's crossing through the origin because it can do that. So if you band limit the signal and then send it through a nonlinearity, what happens is that those side lobes regrow. And this is a really bad thing for straight up QPSK. The side lobes will regrow. This is for rectangular pulse shaping, so it's kind of a worst case scenario. If there was square root raised cosine pulse shaping, then it would be a different scenario, but square root raised cosine is not even a constant envelope, so it's already sensitive to nonlinear amplifiers. This was the original scenario for satellite communications. They wanted to use efficient power amplifiers that were running close to compression to avoid using a lot of energy on board the satellite. You have a question?
two, but maybe one will answer the other.
Okay.
Wouldn't offset QPSK, maybe I'm wrong, wouldn't it use more bandwidth because now you're essentially transitioning twice as often? Or is that wrong?
No, it's wrong. It doesn't make any difference at all.
Because I guess I and Q are still transitioning at the same rate.
Exactly.
But I'm thinking your cosine that you're sending out into the world could transition twice as often now, right?
No, because its symbol period is like this, and the quadrature is just staggered over or shifted over. It's still transitioning, like you said, every symbol time. It's running at half the rate that it would have in the serial communications. So it's more bandwidth efficient. It's half the bandwidth that you would. If you wanted to send 1 gigabit per second with BPSK, you'd use the main low bandwidth would be, if null to null bandwidth would be 2 gigahertz. If it was QPSK, you'd be running each of the data streams at 500 megabits per second.
Right.
And then your null to null bandwidth would be 1 gigahertz wide. And if you stagger it, in theory, it doesn't make any difference. But if you've got a nonlinearity present and you're wanting to band limit the signal slightly, and that's what they were trying to do in the olden days where they had rectangular pulse shaping, they wanted to just keep the main lobe, only have tinier side lobes, so they would filter the signal. And then if you send it into a compressing nonlinear amplifier, it regrows the side lobes like you see on the left. But if you use offset QPSK, it's far less sensitive to the spectral regrowth. That wasn't your question, but I just forced myself to say what I wanted to say.
Can I try to ask it one more time?
Yeah.
Maybe you'll give me the same answer, but
Yeah.
let me just, with normal QPSK, you would have a transition every 1/, every period, right?
Yeah.
Whereas I'm sort of imagining in offset QPSK, you'd have a transition of I, and then a transition of Q, and then a transition of I, and then a transition of Q. So it seems to me like transitions are twice as often.
So I guess this
That's
pic.
maybe what I'm not quite
Yeah, let's look at this picture.
But each individual channel, I guess, is still only transitioning at the bit period.
Yeah, and that's the key, because it's the quadrature, nature of it. The spectra ends up being the sum of the spectra for the in-phase piece and the quadrature piece. So I think that probably answers it. We haven't gotten there yet, but that's showing up further down when we're looking at spectra of these. I think that's the key. This picture got you confused, and rightly so, because you said, oh, it's making transitions every bit time, or every bit serial bit period, whereas up above it's only every symbol period. So here in the lower one they're occurring more frequently. That was what got you hooked, right? But then if you look at the waveforms and say, okay, the in phase still only changes every symbol, quadrature only every symbol, and then if you study how the spectrum gets formed, because of the fact that they're orthogonal, the spectras just add for the in phase and the quadrature. But with the exception, though, being that when you have hang-ups like this with the nonlinear amplifier, then you get the AM to PM and AM to PM conversion, so amplitude converts to phase modulation, and AM to AM also takes place. So that's the spectral regrowth thing. These guys from way back when discovered this early on, and they said, we have to use offset QPSK. So a lot of systems I worked on many years ago was offset QPSK because of this spectral regrowth problem. In handsets, high power amplifiers on satellites are definitely a must, because you want to have low power consumption on board a satellite, right? The satellite is, well, what's the nature of a geostationary satellite? Is it always in the sunlight? It's not always in the sunlight, right? It goes dark. So it has to still be communicating though when we're dark and the satellite's way up in the sky. We still want to use it, so it's running on battery power then, and it's starts recharging when it gets in the sun again. So they want to use power efficient amplifiers. And in a handset, we still have the same problem. We're receiving, no problem. We don't have to worry about power amplifier. I mean, the receiver is a lot less power than the transmitter, but when we're talking or sending data up to a base station or something, we do care about power amplifiers and being able to run them efficiently. So, and the waveforms are more complicated. They maybe wanted to try to use the same idea, but then this got abandoned, I think, for mobile radio, because this is not as spectrally efficient as shaped modulation is. You know, like that's one of the big features of the root raised cosine, is you can make the spectrum very efficient, but then the amplifier can't tolerate. You can't tolerate an amplifier with a lot of nonlinear effects, but nowadays they use pre-distortion techniques. So they pre-distort the waveform so that when it runs through the nonlinearity in the RF circuitry, it distorts it back again, and then it looks normal. So I think the pre-distorter idea is kind of now very commonplace, and us systems engineers can get what we want. We want spectral efficiency. We just have to add in some additional complexity to have a pre-distorter if that's necessary. Or this 5G thing that I started getting introduced to, it has some other things for peak to average ratio in OFDM, because that's one of its bad things for power amplifiers. It has a high peak of its envelope, and so your amplifier has to be able to manage that without clipping or distorting. Most of the time it's not doing that, but then you end up with, again, inefficiency. You guys ever think about that? But that's what comm theory people are always thinking about. How do we get long battery life? Because everybody wants that. I personally don't need it myself because my phone's back on a charger very regularly, but other people are out using their phones continuously throughout the day, and they, I guess, I don't know one of these devices, they have that little battery pack that they can put on their phone to make it last longer. Either of you ever have to use one of those things?
I sometimes bring them on like overnight trips or something.
Okay.
But
And as a backpacking person from a long time ago, haven't been doing very much of that. I just have a little Garmin GPS that uses two AA batteries, and all it does is GPS, so I can track my location and have my maps on there to aid my paper maps, which I always carry. But to use a cell phone as a GPS with maps, to me, is very inefficient because I'm running all those other applications on the phone, and I don't have any use of those when I'm in the backcountry because there's nothing, there's no social media or anything, and there's none of that. All I care about is the one function, the GPS. And that's another thing about phones too, is we now use them in so many different ways, which is good, but all those things take up energy. I guess you can, maybe what they've done now is you can cache things, and I really haven't tried that lately. I know it's very tempting because the phone is your universal box, but I still have my old standalone GPS. So hopefully this made some sense. If you ever are involved with satellite communications, you'll see offset QPSK is very popular. So I'm going to take a break so I can look and see if there's anything good in this notebook that I just discovered about looking at offset QPSK and the simulation engine that I created. So I'm going to stop, pause. So I decided to abandon the notebook that I had, and instead I'm just going to, this notebook will get reposted for the chapter 10 that we're into right now, in the notes. I mean, the book chapter 10, notes chapter, what is it? Chapter 6. So I do have QPSK, and I was just editing all of the labels on here because all these capitals that used to be in here are now lowercase. But here's, I have a function that we will be using in this chapter. It does mary PSK. We haven't seen that defined, but you can set an argument in here. The way I wrote the function is you can set the modulation level to be whatever order, and you can set it equal to 4, and then it's going to do 4 level phase shift keying. So that's what I'm doing, and then I'm just doing a I'm just not doing a scatter plot, but I'm just plotting the modulation. So it is indeed crossing through the origin, just like we said. And then if I, say, throw up a third order Butterworth filter to band limit it, you see that it's having those excursions outside the rectangle. And in particular, if I look just at the envelope, so here I'm looking just at the absolute value, which would be our envelope. This is what leads to the spectral regrowth property when we run it through a compression amplifier. It's because the envelope of the signal is no longer constant because of the filtering. If I was to overlay, I guess why did I even do it that way? If I was to overlay this one, oops, I plotted the wrong thing in the wrong spot. Now I don't know what I did. I thought this was the X from up here. I actually don't know what I did. Maybe I should just not try to do anything. I'll just make things worse. Oh, I know what I did. I didn't rerun this because I was way down the page. That's what my problem is. I reused all the variable names, and that's what my problem is. So I wanted to just point out that if I don't filter the QPSK signal with the rectangular pulse shaping, its envelope is perfectly flat. But by having that little bit of band limiting in there, then I start getting a non-constant envelope, and that's what creates the problems that we were talking about just before the break with the spectral side lobe regrowth. Okay, that's coming up here next. So I dialed way ahead on this. I'm just dialing back to where I was. If we had pulse shaping in there, then, or different types of pulse shaping, our receiver would have the matched filter that we've talked about before, and then we would have to come along with our sampling instance at the maximum eye openings on both the in-phase and the quadrature. And this would be what the block diagram would look like with the decision devices, and then getting back to the 4-phase states, say for QPSK, whereas BPSK we had 2 points, now we have 4 points. And if it was offset QPSK, all that changes is we just would add in, well, yeah, this is offset QPSK. What am I looking at? You can see we're offset, and then the sampling instance have to have a skew factor in there, which takes into account that staggering. I don't know why I don't have that shown in here right now. I'm not actually sure why I did that, period, but that needs to be in there if we want to combine them together, because we don't sample. We sample at okay, I guess I see what's going on here. The way this block diagram was drawn, and I didn't draw it, it samples every bit period in the serial bit stream, but then it's going to only apply that value every other sample to the decision-making device, and that's consistent with this, because if I sample at every bit period, I'm going to get samples at the crossings, but if I stagger it, and that's what's going on in here, the staggering is flipped between the in-phase and quadrature. So no surprise there. We already talked through that, I think, but that's what the match filter receiver would look like. Okay, so we've gone from QPS, straight up QPSK, offset QPSK. The next type of modulation to discuss briefly is minimum shift keying, or MSK. And MSK is still in use in various locations today. It's not in cellular telephony for sure, but it's used in some SATCOM and some other terrestrial types of applications. So what brought people into MSK, and the guy that taught me digital comm first off was a student under Roger Zemer, early in his career. He was very fixated on MSK, so I got a really heavy dose of minimum shift keying early in my life, and then MSK leads to other related things like Gaussian MSK, or GMSK, was used in the GSM, Global System for Mobile Communications. That was a 2G standard, which all countries had. I'm sure Iran had it too. 2G, I don't know if that ever meant anything to you when you were growing up, but it would have been quite a few years ago for 2G. But it was developed by the European community, GSM, and it used Gaussian minimum shift keying. And we'll be getting more into that right now, but we'll get more into the spectral side of it. Both MSK and then its follow-ons were designed to be more bandwidth efficient, is what motivated them. So minimum shift keying would have the original form of minimum shift keying, and there's different variations of minimum shift keying. First off, it's based on staggering again. So you come in with a serial bit stream, and then you demultiplex it into the in-phase and the quadrature. So now the quadrature is on the bottom, which I like better. The first picture was the opposite. But you stagger the quadrature, and then you're applying these pulse shapes. So it's easiest to think just in terms of the in-phase, but it applies equally to the quadrature. It's just, you think of cosine, it's a half cycle of a cosine is what's happening here. So the half cycle of the cosine takes that into account. It does roll continuously in this scheme, but because of the way the bit edges are occurring, it's applying a half cosine shape, either to the positive or negative pulses. And then in the quadrature side, because it's staggered, the sine wave serves that same purpose, because the sine wave is effectively like a cosine wave shifted over by 90 degrees. So the bottom line is we're applying pulse shaping to the rectangular pulse shapes. And then in the receiver, you have to apply that same pulse shape, and this is done as a correlator. So this, when we see something like this, you just have to say this is the correlator. Implementation of the matched filter. The correlator means you multiply times the pulse shape, and then you integrate over that interval to get your matched filter output, and then you make your decisions after that. And you do the same thing on the quadrature side. You just offset differently because it's starting off with it has a staggered bit stream pattern. I'm trying to get down here to the picture of what I've been talking about, and then I'm going to back up to the math. So the top is offset QPSK that we started with before the break, and then when the half sine and half cosine are applied, we get these smoother pulse shapes where we have the shaping on both the in-phase and quadrature. And then that is what gets transmitted. So having this pulse shape changes the spectral shape and makes it more bandwidth efficient. And then you can also go ahead and write the in-phase and quadrature waveforms as an envelope and a phase, and the trig identities can be applied to the in-phase and quadrature. And one of the things that we get out of this, just like before, this is constant, so it's a constant envelope. And not shown here, but right in here, but this is linear phase. So the phase is making a linear phase trajectory as each new bit comes in, whether it be a bit change in the in-phase or bit change in the quadrature. And furthermore, the deviation then is constant. So if you look at the phase that we have in the two different streams there, theta I or theta 1 and theta 2, that the derivative of those, which would be the instantaneous frequency, is constant. So there's some really interesting properties that come out of the shaped modulation. Namely, you get continuous phase, BPSK, QPSK, and offset QPSK, the phase jumps. We were talking about that. It jumps, comes along, reaches a bit time, and it just jumps, one of 4 phase states, or jumps, across the square. So just be thinking in QPSK, you've got 4 values. They can just jump, anywhere, or they can jump by crossing through the middle. BPSK always just goes back and forth. But with MSK, because of this shaping, the fact that we have these linear trajectories of phase, it does something that's very nice. And that is, if you carry this all the way through, take the shaping with the data, which is the product. So these two combine together to be that. And then the in-phase and the quadrature, if you looked at it in terms of the modulated signal, what we're seeing is a continuous phase modulation, so there's no discontinuities in that waveform at the bottom. It also looks like what? Just thinking back to analog modulation from COM1 type material, what does it look like is going on in there?
It looks kind of like phase or FM or phase modulation.
Yeah, exactly. But it's special. There's no discontinuities in phase modulation or in frequency modulation. There's not a guarantee that there might be a discontinuity. When I say a discontinuity, I don't mean that there's a jump, but I mean that two functions would come together rather than smooth, so the derivative is defined equally on both sides of that discontinuity, but it might change in slope, and that would make it susceptible to issues when you filter it and pass it through a nonlinearity. But in this MSK, it's perfectly smooth. There's no discontinuities in it at all. The error probability is identical to that of QPSK or offset QPSK, but the power spectrum is different. So it's more compact, but it's a matter of definition, and we'll get to that. It has a wider main lobe than QPSK does, but the lobes roll off faster because of the smoothness of the phase. And that's
kind of like windowing them?
Yes, it's kind of like windowing. It'll roll off faster. It's a good observation. And that's a desirable feature too in modulation, get it to roll off faster. Now this came along before the popularity of root raised cosine. You know, root raised cosine just dominates in the cellular world right now. It's just what everybody wants to do. But it introduces envelope fluctuations when it does that. OFDM has this peak to average ratio problem. MSK came along during, you know, the satellite modulation theory eras and wanting to be very efficient when power amplification is involved. So it is a form of modulation known as constant envelope. All the information is contained in the phase. It's not, there's no amplitude information that you extract from the signal that carries information or bits. So that's what makes it so advantageous for SATCOM. And I got such a heavy dose of it because my, not my dissertation advisor, Dr. Zemer, but my master's thesis advisor was a friend of Dr. Zemer's. His name was Carl Ryan, and he taught me digital communications during my master's degree. And then I went back and redid things for my doctorate, but my first dose of digital modulation theory was by him, and he was very interested in very high data rate, continuous phase modulation for satellite channels where nonlinearities were present. He was just fixated on that, and he has some patents on MSK, some demodulator architectures that he had graduate students investigate too. Now, why did he have patents and why did he also have graduate students? Well, he was in industry for Motorola Government Electronics, and then he decided he wanted to go teach at Michigan Tech. So that's Michigan Technological University is Michigan School of Mines. So it's an all engineering school. That's where I got my BS and MS. And he came in there and had just left industry because he was getting burned out. I mean, people get burned out on both sides of the coin, whether they're academia or whether they're in industry. I feel like it can happen anywhere, because I feel like I get burned out here at the university because I can't control my behavior and trying to do too many things at once. But he came for a while, and so he had master's degree students mostly doing things for him. And then he went back to industry again, and he went back to where he had sent me to go to work in industry. So I first had him for my master's degree thesis advisor, and he sent me to go work on a project back in industry, and then he decided to move back to Arizona where it was warmer. His wife didn't like the cold and snowy weather of upper Michigan that got not just a few inches like we get around here, but it was 300 inches of snow that would not go away until the end of the winter. You know, we don't have it like that here. In the mountains of Colorado, yes, and you will want to go see that if you haven't seen that. I mean, it piles up. They use the rotary snow plows, and it just, and can you imagine that? 300 inches is a lot, and the snow banks are, you know, like higher than the ceiling is in here along county roads. When they plow the road out, the snow just builds up, and people put structures over their walkways leading up to their house. It's like a dock that you have over water. They put that over land just to raise it up, so that because the snow has gotten so tall that you have to walk up above it to avoid walking through it or digging it all out. His wife didn't like that. She grew up where it was warmer out and never had seen that much snow. And it does make you feel very isolated, especially if you're just at home, and she was at home, so she felt like she had to get back again. But I lived in Arizona, and I felt it was like it was too hot. Living in a desert was just burning me up, so I didn't like that either. I liked the work though. So we'll come back and look at the spectral properties of it, but then sort of the evolution of MSK was the beginning of continuous phase modulation, and this is what my dissertation was on, a form of CPM that we'll get to after we look at just this binary CPM. So continuous phase modulation is started with MSK, and then people went to Gaussian minimum shift keying, or GMSK. And when you model continuous phase modulation, a more abstract way of modeling it, which is good for understanding it, rather than just the MSK was the half cosine and half sine pulse shapes and all that of the in-phase and quadrature. The better way, I think, is to just go straight at it with complex baseband modulation. And then what you're talking about is some function S. And this alpha is a vector of symbols. So it's containing all of the symbols from the past that have been sent into the modulator. So what you get into with this continuous phase modulation is, if you're looking at the carrier phase right here, and you've got this history vector alpha, you've been taking the carrier phase through all these different phase increments over time due to different bits being sent through. So you've got the history that's led up to what is the phase at that point. So that's like your state vector. And then you have the deviation that you apply at each new bit through a pulse shape Q and then a modulation index H. So H is the modulation index, and then Q is the pulse shape. Well, wait a minute. I have it defined down here. I don't need to write that out. So the phase pulse is the integral of the frequency pulse shape G, and that becomes Q, and its area is such, the frequency pulse, its area is such that it's 1/2, or it's normalized to 1/2. So that way, you generally think of the phase deviation that a single bit would apply on this type of GMSK or straight MSK looked at this way would be a 90-degree phase rotation at each serial bit. Whereas with QPSK, remember we would take jumps of 0, 90, or 180 degrees. With staggered or offset QPSK, it would always be 90 degrees. It would be like that or that or that or that. It was never full 180. So GMSK just extends the idea from the MSK idea with a half sine shaping where you can deviate the phase carrier by plus or minus 90 degrees during any new serial bit transition. So you don't think about demultiplexing, you just think about serial modulation. And actually my master thesis advisor created a new name for the modulation, MSK. He called it serial MSK, because rather than thinking of it as a demultiplexed in-phase and quadrature, he just said, just think of it as serial MSK, where you just, every new bit comes in and you deviate the carrier by 90 degrees in some fashion. And then, lo and behold, I mean, what was going on already at that time by people at Bell Labs and other places was multi-H CPM, multi-H continuous phase modulation, and that ended up being what my dissertation was on, was multi-H CPM. So it's just, we'll look at that in a second, but it's very complicated to demodulate multi-H CPM. You need a maximum likelihood sequence estimator, which is a trellis, and we'll be looking at the trellises here in a second too. So that's how come I'm so fixated on modulation, is because I got grown up into that by my advisors. Especially my thesis for my master's degree. I did not do CPM. I was talking about that guy doing it, but instead I was doing optical communications. I was doing pulse quaternary optical modulation, which was putting optical light up in two polarizations and then putting the pulse, the laser pulse, in one of 4 different locations. In polarization 1, it would either be early or late, and then in polarization 2, it would be early or late, and that single pulse was sent in one of those 4 positions. every symbol period. So it was called PQM, pulse quaternary modulation. It's kind of similar to QPSK, where you've got the carrier in one of four states, but in PQM it's non-coherently demodulated, so the light is in one of two time positions and one of two polarizations. Kind of makes sense, doesn't it? You could still get 2 bits per symbol then, and that's what that was. Why did I do any of that? It's because, and why do you do any of this? It's because, well, you picked your own topic. Congratulations, but you might have your advisor give you the topic, right? And that's the situation I was in for both my master's and PhD. My advisor gave me the problem, but I let students give me their ideas, and then I give them feedback and say, if this is what you want to do, I'm fine with it, and I'll try to make it work. But a pretty common scenario is your advisor picks the problem, and then you're an offspring of your advisor because you grew up, extending something that they already were studying. So I went through that, and I got all charged up about certain types of modulation, and then because of the complexity and the inability to build the system that I worked on, because it was just too complicated to demodulate it, I went off and did other stuff because I said, I'm tired of this. I want to do something different. I mean, and you can do that too. It's better. I think it's better to be more diverse. If you just continue doing the same narrow thing, then you're so specialized that what good are you? If that goes away or nobody wants to use it anymore, you're going to have to retrain yourself. So MSK, the rectangular pulse shape frequency pulse shape becomes a phase ramp. So that means that the phase trajectory is a linear trajectory of 90 degrees every serial bit time. So if you take the 2 variations on MSK, which are talked about in the book, which were just different people coming up with different forms of MSK. There was type 1 and type 2. And then there was the serial MSK that my master's thesis advisor developed. And then there were other people that just plain said, we're going to call a new type of modulation CPM. And CPM is, I'd rather just think in terms of CPM because it's just more straightforward. It's what we were just saying. You have the history or the state vector of phase trajectories, and if you're doing a constant modulation index, this is what binary CPM would look like, using rectangular pulse shapes that then, when integrated, are linear trajectories. And so this is how you demodulate CPM. You demodulate it using a trellis type structure, and the darkened path here is what you're trying to discover when you're receiving this waveform. And you have to get your head wrapped around this. The vertical axis is angle, so the phase it's modulo 2 pi, but over the period of time, if you're really wanting to properly demodulate it, you have to unwrap it. So this is like looking at the phase unwrapped, and it's going to just deviate. It could deviate if all the bits were positive. It would keep deviating plus 90 degrees every bit time. And then a while later, it might have some negatives and it'll come back down. But when I first did this, I had a little paper model that I created that was a cylinder. So the cylinder was time on the axes of the cylinder, and then the radial component was phase. So if you think about this wrapping modulo, you could visualize it on a cylinder, and that's what they always said in the papers I was reading. Visualize it on a cylinder, and as time evolves, the phase takes on a trajectory. So that's what the trellis does. And if you use a maximum likelihood sequence estimator, that's what you're doing. You're gathering up all this phase information, and then you trace back through the trellis after you've put this on a trellis in the Viterbi algorithm, and you say, okay, back so many states in time, the trajectory must have been a plus phase ramp or it must have been a minus phase ramp, and then you can finally decode the bits as being plus ones or minus ones. So what does Gaussian MSK do? Gaussian MSK says let's modify the trajectory to be a Gaussian, related to a Gaussian pulse shape. We'll make smoother transitions with the Gaussian pulse shape. And so we're going to have G be a Gaussian function, and this is what it would be then. And also it came into being because GMSK could be created more readily in small portable electronics. And as a matter of fact, you can just use a frequency modulator or voltage controlled oscillator driven by an NRZ bit stream, plus and minus ones, and then you just shape it in this fashion. So you shape through a Gaussian shaped impulse response filter an NRZ bit stream, and then it goes and produces GMSK. And what's significant, I suppose, is my mouse has got the, this is a Logitech mouse. It's operating at 2.4 gigahertz. I don't know if it's Bluetooth or not, but we have a lot of Bluetooth devices out there. So what does Bluetooth use as one of its core modulation types was Gaussian MSK or GMSK modulation. And the cool thing about GMSK is you don't have to modulate it with a trellis in the Viterbi algorithm. You can actually use a limiter discriminator type structure. And I don't know if I have that in the notes right now or not, but you can get away with a less sophisticated demodulator. You get a performance penalty, but it's not that bad. And cellular telephony also took advantage of this in generation 2 with the GMSK. So this is what the frequency pulse looks like, and if you're doing it exact, and this is my modulator in MATLAB for doing the GMSK. I have the exact same function now available in Python. So rather than looking at this code, I'm just going to show it to you live action over here. And I'll look at the spectrum right away too. So I have in the digital comm module, if we drop down in here, there's different types of modulators and demodulators, but under G's, we have GMSK baseband, and that's what I'm using right here. And GMSK baseband, if I go Shift Tab, I can see that I have as my third argument, if I set MSK equal to 0, then it's going to produce just standard MSK, which is the linear phase trajectories. And if I set it equal to 1, then it will, well, maybe it's the other way around. 0 for no shaping, which is standard, and not equal to 0 is GMSK. And then you set in the time bandwidth product of the Gaussian pulse shape. That's the way it's defined in the standards that people use, like in Bluetooth. So time bandwidth product would be 0.35, let's say. So here I've generated them both. I've generated 100,000 symbols in a waveform that's got 10 samples per bit. And then I'm just going to do a power spectral density calculation and plot the power spectral density right here. And GMSK, or MSK, which we haven't seen the spectrum for yet, it's first null rather than being at 0.5, which is what it would be for QPSK. Why is it 0.5? Because we have 2 bits per symbol, or the symbols are twice as long as a bit period. So rather than null to null being 1 and minus 1, it's 1/2 and 1/2 because we're transitioning less frequently. But when we go with MSK, it doesn't land at 0.5, it lands at 3/4. So it's got a wider main lobe, but the side lobes drop off faster. We'll look at that in another plot, but when you add in the Gaussian minimum shift keying, what you notice immediately is that the main lobes are similar, but the side lobes drop off a lot faster with the Gaussian pulse shaping. And this means that waveforms can coexist better, like Bluetooth, for example, can coexist better. But Bluetooth adds another layer of complexity. It adds in frequency hopping, so the signal doesn't stay put. It moves around so that it doesn't land on top of another Bluetooth device. They keep hopping around. Is everybody, did you know that already? You probably did, but you just don't remember it. That Bluetooth avoids local interference by just hopping over a band of frequency, so that you still get interference, but it's not like you're getting whacked. You're getting clear things through, and you just notice that as latency and stuff. So when my mouse sometimes acts up, I'm thinking that there's some other Bluetooth device nearby, and it's just getting clobbered a lot. So it's getting more latency because it can't get updates through. So I put a function in here to plot the trellis to just verify. So there's just unwrapping the phase. There's the MSK with the linear trajectories deviating by pi/2 each bit. And there's what the trellis looks like with the shaping. It's got a different trajectory. It's a smoother trajectory, which leads to more compact spectrum. And what I'm not showing is how a limiter discriminator can work on these. Maybe I'll put that in here. I think I've got it somewhere in here that you can actually get the transitions detected by just sending the signal through a limiter and discriminator that you learn about in COM1, where you can, a discriminator measures the instantaneous frequency of the carrier, so that can recover the bits. It's just not as optimal as the trellis decoder would be, but trellis decoders are complicated. Limiter discriminator can be in a battery-powered device, a kid's toy, whatever. I mean, it's GMSK has been fairly popular, or some variation on GMSK. I'm just about out of time. Yeah, here's the comparison. GMSK, MSK, and QPSK. And offset QPSK would be the same as QPSK without any band limiting. So which looks the most attractive if you had to pick between those three? GMSK. And it can be done inexpensively with not the same optimum performance. But so this is what was used in Generation 2 cellular, 0.35 GMSK. So I thought I had multi-H in here, but now I don't see it. I guess I don't have multi-H in here. The next thing up is now switching gears, and I'm not going to get into this, but I'm just going to say we're now going to go over to the signal space concept. Quit discussing things one at a time, but come up with a general structure that's good for a lot of digital modulation. And this will be signal space interpretation, so it's going to bring in linear algebra. And it also relates to statistical decision theory, which is in chapter 11, hypothesis testing. And so we're going to end up with the idea of having bases functions to describe digital modulation, and then we'll have the projection along a particular basis. So the starting point is going to be nice and simple, and it's really the one that goes the whole distance, and that is just in phase and quadrature. So we'll have a two-dimensional space is what we're going to have, so we can define two-dimensional. But this same idea can be used for higher order modulation like FSK, for example. Each new tone can be another basis function. And we assume the tones are orthogonal, and you can have n tones. So the same signal space idea is useful in other senses too. But most of the schemes we're going to look at will just be two-dimensional but they can be a concatenation of things too, like OFDM. Each of the subcarriers is a two-dimensional space in phase and quadrature, but then it's concatenated across a band of frequencies that are nominally orthogonal to each other too. So is it cool? I don't know. For me it is, because I like modulation theory and how you can just keep, using mathematics to represent things. Well, I'm going to have to stop. I know the class doesn't come in today, but I've got to get up for my 11 o'clock call to California. Any questions? I realize I haven't graded papers. I'm really guilty of that. I want to keep you moving though, and you can start looking at the first couple of problems. The third one is the one where I'm, not certain yet. I guess I'm going to stop the recording though and have a little short extra discussion here.